All right, CUE champions, listen up. We're about to tackle a topic that looks easy but is actually one of the biggest rank killers in chemical kinetics, molecularity. Seriously, getting this right in the next few minutes is going to put you so far ahead of the curve. Ready? Let's jump in. So take a look at this reaction. What's your first instinct? Probably to just add up the numbers on the left, right? Well, that is the exact trap almost everyone falls for. Stick with me, and by the end of this, you'll see exactly why that's wrong, and you'll never make that mistake again. I promise. So what in the world is molecularity anyway? Forget the complicated textbook definition for a minute. Let's just think about what's happening on the tiniest, most basic level. It's really just a collision story. Okay, the absolute keyword on this slide is simultaneously. That's the whole game. Molecularity is literally just counting how many particles, atoms, molecules, whatever, have to smash into each other at the exact same instant for a reaction to kick off. But, and this is a huge but, this only counts for one single elementary step of a reaction. Let's just break it down real simple. If you've got one particle that just decides to change or break apart all on its own, we call that unimolecular. If two particles have to collide, which, by the way, is the most common scenario, that's bimolecular. And if three particles somehow manage to all hit each other at the same time, that's termolecular. And man, is it rare. I mean, think about it. Trying to get three things to meet at the exact same spot at the exact same time, that's super tough. And that right there tells you the limit. The highest molecularity you will ever practically deal with is 3. And why is that? Because the chances of 4 or 5 or more particles all colliding perfectly at the same microsecond, it's basically 0. It's pretty much impossible. That's a great little fact to lock away for the exam. Okay, now for the part that's going to save you so many marks. I want you to think of these as the unbreakable, non-negotiable laws of molecular physics. This is your cheat code to beat those tricky exam questions. So here's what you have to remember. Molecularity is always a positive whole number. 1, 2, or maybe 3. It can't be 0, right? Because you need at least one particle for something to happen. It can't be negative, and it can't be a fraction. It's a theoretical idea we get from the reaction mechanism. And this is the most important rule, the one everybody messes up. It only works for elementary reactions. All right, let's hit pause for a second. Let your brain chew on this. Why can't you have a molecularity of like 1.5? Just think about what it means physically. Can you have half a molecule crash into another one? No way. It's counting real things, real particles. So the rule makes total sense when you think of it that way. Okay, stop. Quick attention reset. We're about to pull the curtain back on the #1 mistake that students make on the CUET exam with this topic. This is the big one. Here it is. This is the trap. The examiners love to give you a big, complicated, balanced equation, and they are tempting you, just daring you, to add up the coefficients on the left. You cannot do it. Those numbers, the stoichiometric coefficients, they just tell you the overall recipe for the reaction, not how many particles are colliding in any one step. For complex reactions, they are totally different things. And that brings us to the main event, the classic showdown, molecularity versus reaction order. Nailing the difference between these two is absolutely everything. So here's the side-by-side. Look at the huge differences here. Molecularity is all theory. It comes from a proposed mechanism. Reaction order, that's all about experiments. You have to get it from the rate law. Molecularity is always a nice, clean, positive integer. But order can be anything. It can be 0, it can be a whole number, it can even be a fraction. And here's the clincher. Molecularity is for one tiny elementary step, while order describes the whole shebang, the overall reaction. But there is one special case, one single moment where these two different worlds line up perfectly for a simple, one-step elementary reaction, and only for an elementary reaction, the molecularity is actually equal to the order. This is the golden rule. If the question flat out tells you it's an elementary reaction, then your life just got a whole lot easier. All right, you've got the theory down. Now let's see if you can put it to work. Time for a little mini challenge to check your understanding. Okay, check this out. We've got the reaction 2NO gives you N2O2. Now here's the most important clue in the whole question. It is an elementary reaction. So what's the molecularity? Is it 1, 2, or can't we figure it out? Take a second, lock in your answer. If you picked B, 2, you nailed it. Fantastic. Because we know it's an elementary reaction, we are allowed to look at the coefficient. We have two molecules of NO reacting, which means two particles are colliding. Simple as that. It's bimolecular. See how easy it is when you know the rule? Okay, let's pause and go a little deeper. What if I didn't tell you this was elementary? What if this was some big, complex reaction that just happened to have this as its final balanced equation? Could you still look at that 2 and say the molecularity is 2? The answer is a huge, definite no. And that brings us full circle, right back to the problem we started with. Okay, final attention reset. Let's bring this all together. It is time to finally close that loop we opened at the very beginning and crack that first question for good. Remember that first reaction I showed you? The one where 99% of students get it wrong? Well, here's the secret they don't tell you. It's a complex reaction. It doesn't happen in one go. It happens in a bunch of little steps. It is not an elementary process at all. And this right here is the ultimate takeaway. This is the sentence that is going to save you on your exam. For any complex reaction, the overall balanced equation tells you absolutely nothing about the molecularity of any of its steps. You cannot figure it out from that information. That is the trap, and now you know how to step right over it. So let's do a super quick recap of your rank-boosting summary. 1, molecularity is how many particles collide in one elementary step. 2, it's always a positive whole number, 1, 2, or 3. 3, it's a theoretical idea. And 4, the most important one, never, ever, ever guess it from a balanced equation unless you are told point blank that the reaction is elementary. So I'm going to leave you with this one final thought. From this moment on, whenever you see a question that asks about molecularity, what is the very first question that needs to fire off in your brain? It should be, is this reaction elementary or complex? Just asking yourself that one question is the difference between getting it right and falling for the most common trap in the book. You've got this.